Well, good evening and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik, and it's great to have you here, both in person as well as want to welcome those watching on the live stream. During January and February, we really peel back the number of programs we have, mostly because of the weather, and we will resume our weekly Friday night programs starting in March. March 7th will be our first return to weekly programming. But just for those people that are here, who's here for the first time or hasn't been here since their 4th grade field trip? Okay, a couple of people. All right, great. Also, who here are members? All right. Yes, actually, some of the first timers are members, so that's great. Welcome, welcome. What I'd like to let people know is that people who are members of Kopernik have a very valuable piece of paper in their wallet or purse, and it's because a Kopernik membership actually not only gets you into Kopernik on any Friday night, but also we belong to what's called the ASTC, Association of Science and Technology Centers, and so our Kopernik membership actually gets you into the Robeson Museum and Science Center, the Museum of the Earth, Ithaca Science Center, Museum of Science and Technology up in Syracuse, the Franklin Institute down in Philly, or the Intrepid down in New York City. So, and you get in for free with those. So if you like this kind of place, getting a Kopernik membership can actually save you a lot of money, and you have a great opportunity to engage in science and technology. So we just finished our 50th year of being a STEM education facility. We had a big gala back in October, and we are now starting to set our sights on the next 50 years. We've actually, we're announcing a Reach for the Stars campaign where we're looking to expand the facility, expand the technology that we offer here, as well as hire more teachers and do more outreach, more STEM outreach. We're looking to really get more people engaged in especially young people engaged, but the other piece that we do more than just reach out to young people. This is really like these Friday night programs are really aimed at lifelong learning, and so it's great to see the adults in here, but also the youth that are in here. I want you to see there are adults here that are still learning. So yes, education doesn't stop at 12th grade or at the end of college. It should really be a lifelong pursuit. So if you go to our website, you can always find out what's coming on, what's coming up next. For us, the next major opportunity for us will be our Winter Star Party. So usually right around Kopernik's birthday, Kopernik's birthday was February 19th, and due to some scheduling, we've moved it, well, we didn't move his birthday, but we're moving our Winter Star Party to March 1st. And it'll be a big event. It's very, very well attended. We'll have a great speaker. We always got to have cupcakes, to celebrate Kopernik's birthday. And so we invite you to come plug into that. One of the things I'd mentioned earlier that, we are doing live streaming. And so back in 2020, we had to stop doing our public programs because of COVID. We couldn't put people in a room again. So we figured, okay, we'll just wait a couple of weeks for this COVID thing to blow over, and well, that didn't exactly play out in our favor. So after about a month and a half, we said, look, we have all these speakers lined up. Why don't we just have them zoom into here, and then we'll just put them back out on our YouTube channel? And so that's what we do now. Even though we're now gathering again in person, we found that those live streams have been very popular. We now have actually close to 14,000 subscribers. And not only do they plug into these Friday night programs, but we've done other programs as well. We've done meteor showers, we've done lunar and solar eclipses. We've also done some reaction, sort of watch parties whenever there've been a particularly special launch or return to Earth of astronauts, or in this case, I think did we do the James Webb? I'm not. Yeah. Oh yeah, but What's great about it is we take the NASA feed, but then also in the chat we get people are just chatting back and forth. So it really is a watch party, and we've had a lot of fun with that live stream. What's also been fun was the people that's plugged into the live stream initially. When we finally started doing this in person, we actually got to meet them in person. But our live stream reaches literally around the world. There are people from England that'll be watching. Very often there's Lindsay from Adelaide, Australia, is actually eating her breakfast right now in Adelaide watching our program. So if you're out there, Lindsay, good morning. Bon appetit. Along with our Friday night programs, we do a lot of school outreach, school programs, but also have a very extensive summer camp program. So this is for summer camp for kids that are as young as entering second grade through high school. And these are week-long camps in the summer. We'll be announcing them hopefully in March, mid-March, what we're offering. And they're always they're hands-on, a lot of fun, and you get to meet other students that are similarly inclined, and some great friendships often result from that. But again, for me, one of the things I really enjoy are these Friday night programs because it's an opportunity for us to learn, continue our education. And not everything we do is about astronomy, although tonight's program is about astronomy. We've had people from the National Weather Service talk about tornadoes. We've had a professor from Binghamton University talk about the physics of music. Why does a violin, an oboe, and a trumpet all sound different when they play the same note? And so just learning about how the world works is what we're trying to sort of convey here. So, but we have a good opportunity, I think, to do some observing tonight. And the longer I talk, the shorter the observing will be. So I'm going to stop talking, and I'm going to turn this over to Jenny Cartie. He is one of our Kopernik educators, also our live stream astronomer. And so Jenny, we'll turn it over to you.
All right, thank you. Hello, everyone. I'm going to come right over here. I'm also going to, could you hand me those posters, Drew, that I have on the chair there? I will make use of those. I have a little giveaway, but not yet. Not yet. Later. Okay. So, yes, welcome to Kopernik tonight. And what's amazing, leading up to today and tonight, watching our clear sky chart, which is available on our website. It's the best way to get an idea of what our weather is like up here on the hill, because it will range. We do sometimes get above the clouds here up at our altitude. So sometimes that's the benefit of choosing the second tallest peak in the area. But yeah, leading up to tonight, it was showing clouds throughout the week. And then there's this little window tonight that's clear. So, and when I drove up here this evening, yep, I was seeing the planets out. We'll certainly talk about those. There's quite a lot of activity here in the winter skies. And we're actually ending the winter season with a nice dramatic event. So let's get into it. So what are we talking about tonight? Well, with our Skies program, I always like to discuss the ABCs of stargazing. And just out of curiosity, raise your hand if this is your first time at Kopernik. Oh, there's a good amount of you. Perfect. So this will be brand new to you then, though you may be familiar with some of the terminology. And it's just, what do you need? What are the tools you need to understand astronomy at a basic level? So that's the first part. Then we get into what can we see in the sky this time of year, and some observing tools that you can use either at home or when you come back to Kopernik. You could use them tonight, possibly. So that's the breakdown of what we're talking about. Let's get right into the ABCs of stargazing. So we're literally going to go A, B, C, starting with A. A is for angular size and distance. Now, when we think angular size, think of an angle. What do we measure? When we measure an angle, what units do we use? Yeah, degrees. So we're going to measure the angular size of an object in the sky. Most of the objects are less than a degree, because a lot of them are stars, right? Very tiny points in the sky. But some objects are bigger, though not as big as you might think. So let me show you a tool that you can use to measure angular size and distance. It's not that bad, because you have the tool right here. So the trick to this, though, is that your apparent size of your hand and your fingers are going to change depending on how close they are to your face, right? This is a lot bigger, holding up your pinky here. It's a lot bigger right up close to your face versus arms stretched out. So the way this works is it's your arms stretched out. Okay, so that first one, measuring 1 degree with your pinky out, arms stretched all the way out, the width of your pinky measures 1 degree in the sky. Now, if you held up your pinky and try to cover the moon in the sky, you'd be able to do it, because the width of your pinky is bigger than the width of the moon in the sky. So the moon is not as big as you think. It is the largest object in the sky next to the sun. They're about the same size. That's why we can have eclipses like we had last year. Total eclipses. But it's about the size of the width of your pinky nail stretched out. It's about half a degree rather than a full degree. So that's the context. Everything else is smaller than that, at least of the solar system objects. There are some deep field objects, like a galaxy, the Andromeda Galaxy we'll talk about later, that are about 3 degrees across in total. So that gives you a little hint of what's to come. Next up, 3 fingers. 3 fingers stretched out. That is 5 degrees across. Measuring objects. At this point, we're not talking so much about objects that are 5 degrees across, but the distance between objects in the sky. And that's where these larger figures come in handy. Going to the 10 degrees, a fist with arm's length. So 10 degrees across. And then finally, you have your pinky and your index finger. And this one's tricky because it depends, like, right, where you're holding it. Everyone's spider people out there. Yeah, you want to stretch them out a little and just get a rough approximation of what you're seeing there. It's kind of as far as you can stretch them apart. And that's your 15-degree width at arm's length. All right, so that gives you some good coverage. And at that point, you're able to start measuring. The cool thing is you can just rotate your wrist to double up. Just keep it pointed at a star, and then you can double up on the other side and start measuring the distance between objects. And that helps when you're trying to point something out or explain where something is to the person next to you that might be observing with you. This will also tie into our C in just a bit. So you can measure the distance between objects, and you can measure the size of objects with angular distance. So yes, use this handy trick. All right, next up is our B. B is for brightness. Now, brightness in astronomy we call magnitude. And you'll hear a couple of different kinds of magnitude. In visual astronomy, the most important one is apparent magnitude. What does it look like when you're viewing the sky from the ground, and how does everything compare? The other version of magnitude is absolute, meaning if you could collect all these objects and put them at the same exact distance in the sky, how would they compare? So we're going to talk about apparent. And I have this table here, this line chart, to explain how we measure magnitude. And when you first look at it, you're going to go, what? Because the sun is all the way to the left, right? No, left. And so the sun is on the negative side of this chart. That seems odd, right? Well, that's a trend in astronomy. Things don't make sense sometimes. I'll explain why in just a moment, but let's just look at this chart. Look at the table. We have very bright on the left. We have very faint on the right. We have some kind of number system that's gauging these two from bright to faint. And we have our 0 in the middle. So you'd think, like, okay, if you're going to do it this way, maybe set the sun at 0 and just count up if you're going to make it unintuitive. But the reason this is opposite to how we'd think is because when stars were measured very early on in the field of astronomy, they measured them as first magnitude, second magnitude, third magnitude, fourth magnitude. They were ranking them. So a first magnitude star would be brighter than a second magnitude star, and so on. So as the field of astronomy developed, so too did our understanding of how bright these objects are, and we realized we needed a better system to measure them. And that's where this magnitude chart came in. They kept the ranking, and for the brighter objects, they just pushed them into the negative side of the chart. So it kind of shows astronomy is one of the oldest sciences. And so there's legacy there that just built up over time, and that's why it appears unintuitive. So let's look down the chart now that we understand negative numbers are brighter. The sun is out there towards negative 30. That's going to be the brightest object, the brightest apparent magnitude object we'll see. Then you get to the moon. Then you get to some planets. Jupiter is going to be placed around a negative 3 or so. It does change depending on our distance from the object. But yeah, around a negative 3. Interestingly, we do have a decent star to mark that 0 point, and it's the bright blue star Vega. Fairly young star. If you're a fan of the movie Contact, that's the star that the signal comes from. And that's our 0 marker. Then we go up towards around a positive 4. That's a galaxy, the Andromeda galaxy. Notice that comes in before the faintest naked eye object, meaning unaided eye. You're not using binoculars, telescopes, you're just looking up in the sky with your eye. That means you can see a galaxy with your eye. Beyond the Milky Way, our own galaxy, you can see Andromeda in the sky, and if it's clear enough tonight, we should be able to do that. We can point it out to you. It gets dark enough up here, especially when there's no moon in the way, that you can see that galaxy. Then we go beyond that point, faintest naked eye objects. This is where you need to bring in a scope. Something like the Ring Nebula, a lot of smaller deep sky objects, meaning objects, starry objects, nebula, which are either star-forming regions or where stars have died. Those are all going to be too faint to spot with your eye, and you'll need a telescope. And then cameras can do even more. We'll touch on that a little later, too. And then as you go further and further and fainter, that's where you need to get something like the Hubble Space Telescope or the James Webb Space Telescope, where you'll see the faintest objects. In fact, you reach a point where you stop seeing visible light and you start seeing infrared light. That's what the James Webb Space Telescope does. All right, so that's magnitude. And we'll be referring back to this one as well throughout the talk. C is for coordinates. And we're going to talk about 2 coordinate systems today. The first one is going to, I think, make a fair bit more sense because it's relative to you. The second one is a little more complex, but very important for things like our telescopes out in the observatory. So, the first one, we're just going to skip it? No, we can't do that. The first one, altitude azimuth coordinates, or alt-az. Your basic beginner telescope is going to base itself off an altitude azimuth system. That's where you can just swivel the telescope, you can rotate it around along a base, and then you can point it up and down as well. Swiveling around is your azimuth, and pointing up and down is your altitude. And you can see that here, because we can use altitude azimuth system easily as observers. So at any point looking on the surface of the Earth, looking up at the sky, so here's our observers here. You can map out an azimuth based on the compass directions. So looking around you, notice we're measuring in degrees. You can use your handy tool to mark these out. Your north, good to have a compass, is 0 degrees. East is 90 degrees. See how we're rotating around. South is 180 and west is 270, and then full 360 brings you back to 0 degrees north. That's your azimuth measurement. And then you have your altitude measurement. So no matter where you are along the azimuth, you can measure from 0 degrees on the horizon. So where the ground meets the sky, that's your 0 degree marker. And then climbing up, 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 up until you reach zenith. Zenith is your 90 degree marker. And again there, you can use your large 15 degree marker and just count up, up, up to get your 90 degrees. All right, so that's as an observer, we're on the ground looking up at the sky. But there's a problem with this method in that it's relative to you. So if you're looking up at a star in the sky, like Sirius. Sirius is the brightest star in the sky this time of year. And you measure where it is. You have a compass, you're measuring exactly where it is in altitude and azimuth. It doesn't even take an hour. In the next 10 minutes or so, you'll be able to measure a different altitude and azimuth because that star will have moved across the sky. Now, what drives that? What is driving that motion of the star? Yeah?
Earth's rotation.
Exactly, yes. Earth's rotation. So we can come over here, and we have Earth here, and it spins on its axis. And in doing that, we have day to night, and we have the motion, apparent motion of the stars across the sky. So the coordinate of that object will change in the very short term using alt-as. So this is good for moment to moment. Not so good if you want to give that star in the sky a very specific coordinate. All right, so that's where this other system comes in. Equatorial. And equatorial coordinates are what all of our telescopes in the domes outside use. Advanced telescopes use equatorial mounts. And that's because they're really useful for tracking. Makes sense, right? With this system, compared to the other, you're able to give an object specific coordinates over a longer term. Well, let's think about that. We have this figure up front. But the trouble is, you look at this figure in 2 dimensions, you're like, what is going on? There's lines everywhere. It's kind of hard to convey this accurately in 2 dimensions. So let's go to 3 dimensions. That's what we have this globe for. So I'll come around and show everyone this in just a moment. But what this is, up here we have an Earth globe, and we have a sky globe. All right? So this is the sky if you could view it from the outside. Now, that doesn't really make sense. Early on, it did. To the first astronomers, this is what the universe was like. It was this globe of stars around the Earth. Now we know that's not the case. Space is more expansive, but this model still works for an observer here on our planet. So this globe is the Earth and this sky combined. So you have a little Earth in the middle that can spin around. I can reach my hand in there and spin it around. And you have the star globe on the outside. They call this the celestial sphere. So you can look at this in one of two ways. I can rotate the sky, or I can rotate the Earth, which is more accurate, right? Rotating the Earth is actually spinning where the star field stays fixed. So at least over the course of a human lifetime, you will not notice the stars move. They are changing ever so slightly on their journey through our galaxy, but not enough for us to care too much from an observer's point of view. So for us, the star field stays fixed throughout our lives, and the Earth keeps on spinning every day, going from day to night and revealing those stars. The stars will change through the seasons, and that's another talk entirely, but we might touch on that when we visit our tool of the day, our software, the app we'll look at. But let me come around the room and show you this. You do have a little sun out there too, out here. You can change that as well, as if the sun was moving around the Earth. Again, not accurate, but from a visual standpoint, an observing standpoint, that is what that would look like in our sky. But the star field is staying fixed, and the Earth is spinning on. And because our star field stays fixed in a equatorial coordinate system, we can say that star has this specific coordinate. And we won't go into this too much, but we have two coordinates going on here. You see the celestial equator going around. Another way to think about this is actually taking Earth's latitude and longitude and projecting it out into the star field. So you have two measurements here. You have declination up there measured in degrees, and then down here you have right ascension. So this is more complex, and we could talk about it for a while, but we'll leave it there for now. Just know that that's how we give objects in the sky specific coordinates. It works for the stars, not so much for planets, though, because what are the planets doing? Yeah. Exactly, they're orbiting around the sun. And because they orbit around the sun, they will change their equatorial coordinates on top of their altitude and azimuth coordinates. Okay, let's carry on from C and jump into one of our primary tools of the day, which is Stellarium. And to do that, I'm going to hop right here. Actually, let me show you the base website first. If you go to stellarium.org, you'll come to this page, which features download links for Linux, for Mac, and for Windows. There is also an app on the App Store and on the Google Play Store. You can download for Stellarium. There are free versions for it. You can also use the web-based version, which for simplicity, that's what I'm going to show you. When you use the web-based version, you just load right into a web application. And it will ask if you want to allow it to know your location. If you choose to say no, you just have to input it manually. You can also see on the side there Stellarium Mobile for those two app stores. But we're set up. What's our notification saying here? Oh, cookie, that's fine. Cookies are good, right? All right, so it's telling you we're at Kopernik Observatory and Science Center, but if you needed to set your location, you just come down here and search for it. All right. The The downloadable tool is more complex, so if you just want to start simple, the web version's the way to go, or the app version. And like we can do things just coming down here to constellations and artwork to show you all the constellations in the sky right now. We can talk about those in a couple minutes. We'll turn them off for now. You can also do things like turn off the atmosphere, which in some ways we'd love to be able to do from an astronomical standpoint. Biological standpoint, not so much. But you can do that to show you what it would be like without the sky glow effect you get from brighter objects like the moon or from just light pollution in general. You can turn off the ground too to see what's below the horizon. But here's where we have our two grids we can put in the sky. Now when we put both of them, things get crazy. But it's interesting to see the two overlaid on top of each other. Let's look at one at a time though. Turning off the equatorial so that we just see the azimuthal grid. Our 0 degree marker is the horizon. And climbing up to zenith is 90 degrees. Remember, going around from north, that's our 0 degree marker in azimuth, east, south, west, and then back to north. That's your full 360. So if we travel through time, notice, let's go this way. This grid stays fixed as we travel through the hours of this evening, but the objects move within it, showing you we can't use it to give you exact coordinates over a longer period of time. But great for moment to moment. If we turn off this grid and turn on equatorial, notice the top of this grid lines up with this star. See the name of that star? That's Polaris. What's the other name for Polaris? Yeah. The North Star. Yes, very good. So the North Star points due north 24/7 throughout the entire year. It does not change its location in the sky except for a tiny little swivel in a circle, and that allows us to use it as a guiding star. We can use it as a compass effectively. So what's also neat about this, you can kind of mix the two coordinates together, and if you measured from horizon to Polaris in degrees, your altitude measurement, that would equal our latitude for our area, which is about 42 degrees. So you can find out your latitude using the North Star with a solid view of the horizon. Okay. If we travel through time, though, same thing with the equatorial grid. Notice the stars stay fixed. The grid rotates with the stars. So this is relative to the Earth's rotation. Okay. Back to current time. And we'll turn that off for now. All right, let's go back here. I gotta bring it over this way. Okay, and we'll come back here. All right, now we'll get into what can we see in the sky this winter. What's out there? I want to touch on this first, the International Space Station. And this is something you can see regularly throughout the year even. And there are some good flybys happening this weekend, so I want to emphasize those. The ISS is the largest structure orbiting Earth, or largest human-made structure. It's about the size of a football field, primarily because of those giant solar panels. And this is where astronauts have gone over the past couple decades. If you've heard of astronauts going up in a spaceship, more often than not, they're going up to the ISS. And there's always been someone on the ISS for the last 20 years. What's fascinating about this, too, is it orbits the Earth once every 90 minutes. Super fast. It orbits around 250 miles above the Earth, a little lower than that, once every 90 minutes at a speed of 17,500 miles per hour. So it's zooming around the Earth. So the astronauts literally look down out of their window in what's called the cupola, and they will see Earth below them, and all the landscapes change, flying over oceans. There's some great live streams you can look at that NASA puts out that shows you what those cameras are seeing on the ISS. And at that speed, you could travel from New York City to Los Angeles in less than 9 minutes. Super fast. All right. So that's what the ISS is doing, and when it flies overhead in your area, you'll see it as a point of light in the sky, not too different from a star. It doesn't twinkle. It's a pretty solid point of light. Honestly, more like a planet. And it's going to move really quick across the sky over the course of a few minutes. And there are some flyovers coming up. So tonight there was one. We missed that one. It was a pretty bright one, too. These are negative numbers, right? So these are about the brightness of planets, the brighter planets like Jupiter. So a negative 2.5. And it's showing you the start, highest point, and end time. So it started at 6:12 p.m. at an altitude of 10 degrees. Raise up your 10-degree measurement on your hand. What was that, 10 degrees? Yes, the fist. So that's your 10-degree. And it was in the western sky. And then you come down here. I should be using the mouse so people on the live stream can see. Then you come down to highest point. What's the highest altitude? 34 degrees at 6:15 p.m. in the north-northwest, and 19 degrees at 6:17 p.m. So that's when it ended, and it disappeared. Notice it doesn't make it all the way across the sky. It's still pretty high up there. But just like we have day and night here on Earth, eventually the ISS will enter the Earth's shadow, and then it's nighttime in the ISS for a very short period. Thankfully, there aren't too many windows on the ISS, so they can get cozy in their little cubbies and when they need to sleep. All right, next up, tomorrow is a good opportunity if it's clear. Starting at 7:02 p.m., going all the way to 7:04. And I'd say the 19th, even a little longer, giving you more opportunity. A higher altitude flyover as well, and even a little brighter than tomorrow. So maybe try for the 19th. Again, if we have clear skies. There is a tool you can visit. In fact, I'm going to show you both ISS tools at the same time. So let me bring you to this slide as well. We're going to take a look at this too. Who is on board the ISS at the moment? So let me show you those. All right, so let's just come around here. This is Heavens Above. This is one option that you can use. And I thought I had this set up, but I guess not. Let's go to Vestal. There we go, and we'll update our location. You do that in the upper right here. And then you get this page where you can link to the ISS, and it will show you the visible flyovers. If we zoom in here, you'll see those three I mentioned right off the bat. Tonight, tomorrow, and Sunday. Okay, so you can use this tool to find out when it's going to fly over. The ISS will also appear in apps like Stellarium. So you can do it, you can track it there, but this is a good place to start so you can see exactly when it's going to happen. Then we can come to who is in space. This is a great website. It's very literal. Who is in space? There's 10 humans in space right now. And you can go through and find out who's there based on the missions that flew up. Now, these two were not intending to be in space as long as they've been. This is the crew from the Starliner spacecraft from Boeing. And they launched back in June. They are supposed to be there for a week. They've been there for 226 days. Unfortunately, NASA was not confident in the Starliner at that time, and just to ensure the astronauts' safety, they postponed their return to Earth. And they've actually postponed it a couple times now. I think it's scheduled possibly for March or April at this point, getting postponed from February, which was the original return. So yeah, they've had to change their schedules quite a bit, expecting a week. But they're both seasoned astronauts. They're not unfamiliar with this and being on board the ISS. You can see their mission, their total time in space down here. Butch Wilmore has been in space total for 404 days, and Sunita Williams has been there for 548 days in total mission time. So we have 2 there on the ISS. We have 3 from the ISS Soyuz MS-26 mission that launched September 11th. And there's 2 cosmonauts and 1 NASA astronaut. And then scrolling down again, there's a couple from SpaceX Crew 9. Usually the crew missions are larger. And this one launched September 28th of last year. Given that Butch and Sunny were there unexpectedly, I think they did have to change this a bit. But the SpaceX crew often launches with 4 astronauts on board. So these ones launched from the US, and it is a NASA astronaut and a cosmonaut. And you can also see there's 3 more people in space. There's another space station out there, the Chinese space station Tiangong. And these 3 astronauts launched October 29th of last year. So 2 active stations and totaling 10 people in space. So that's a nice tool too. Gives you a rundown of what missions most recently launched. For now, that's what's active, but there are moon missions starting to ramp up, and there's even a future space station planned by NASA, the Lunar Gateway. So astronauts will be visiting that on top of visiting the surface of the moon through the Artemis program in the coming years. So this will change that, but otherwise all astronauts are going to low Earth orbit at the moment. Okay, let's hop back here. I'm just going to say, don't show me that anymore. And we'll go full screen. All right, it's carrying on. So, the solar system. I would say this is probably the, as far as what's out in the winter sky, this is the highlight moment for it because there's a lot of activity. Now, starting with the sun, last year was certainly the year of the sun, culminating in, starting with the solar eclipse in April, hitting solar maximum back in October. NASA confirmed that we are officially in the higher activity period of the sun. It goes in a solar cycle of about 11 years from peak to peak. We're at that peak now, and it could last about a year. So that's our solar maximum from 2024 to 2025. The other neat thing about closing out the year of the sun last year was the Parker Solar Probe got closer to the sun than any human-made object ever before, back on December 24th, I believe that was. So it basically touched the outer corona of the sun, and it survived. They weren't 100% sure it would successfully make it out of that, but it did. And so it's going to continue its mission and get closer again. And that's a very successful spacecraft studying the sun during a very important period of solar maximum. One word of caution here is do not view the sun without the right equipment. Here at Kopernik, we have special solar filters for our telescopes that allow us to safely view it. But come to a place like Kopernik to safely observe. Very dangerous to just look up at the sun with just your eyes, and even more dangerous with telescopes or binoculars. If you're wondering what's going on in this image of the sun, this is a filtered image showing you the sunspots across the surface. And that's the major marker for what determines solar maximum. As we reach solar maximum, we get more and more of these spots. They represent magnetic storms on the sun. The bigger those storms are, the more chance for very large coronal mass ejections. And when you get a CME, a coronal mass ejection from the sun, it throws off a bunch of material towards Earth. Not all the time, but if it happens to be pointing towards us, it throws it off towards Earth, and there's a risk to that in terms of our communications and power grid. But if we make it through that, and usually it's not a problem, we get northern lights down here in New York. And I have a video for that showing you what that activity looked like back on, I think this was the August 12th geomagnetic storm. And this is Kopernik right down here. And you see the northern lights flying above the observatory there. If you're wondering what, actually there was a meteor there, which pops up right around here. It flashes across the screen. There it goes. But if you're wondering what these are, that's a little abnormal to see that much material flying through our atmosphere, or flying up just beyond it. There was a rocket that had exploded around that time that didn't make it, and most likely that was debris from that mission. That was my only guess, because I'm not used to seeing anything like that, but it does add a nice effect, even though that's all human-made material up there. All right, so that's the northern lights, and we can expect more northern lights to show up here in New York during this maximum period. So if you haven't seen them yet, or if you want to see them again, be on the lookout. Best place to go is spaceweather.com. They have really good updates there that will inform you of future storms. Now, next up, every single month, we have the opportunity to see the full cycle of the moon. Sometimes we even get to see 2 full moons, which is the whole idea of the blue moon, because this comes in at just under average month. And that's the lunar cycle. So that means from new moon to full moon and all the way back to new moon, that's 29 and a half days. So that gives you the chance to see all the phases of the moon during that cycle. Crescent moon, your half moon, and so on. Best way to observe the moon? I mean, easy way to do it is just with your eyes. You can see the contrast, the differing brighter parts of the moon, which represent the crater regions, versus the darker parts, which we call mare or seas. Of course, they're not seas of water, but they were once seas of lava during the moon's formation and era of heavy bombardment. So those are flatter, smoother regions on the moon. They were the original landing locations for the Apollo missions. Now, during Artemis, they're going to land down here at the South Pole. Very cratered region, but there's a reason they're going there, and that's because there is water at the South Pole. Not liquid water, a special kind of crystallized ice water in these deep craters. And where you find water, in this case, you're not looking for life so much. In this case, you're looking for making rocket fuel. Because if you can make rocket fuel on the moon, that's all rocket fuel is hydrogen and oxygen. So you just need water for that. you can not take as much with you when you first go there. So that's the power of water, at least on the moon, and that's why they want to explore there. So Artemis will be landing at the South Pole. Now, here's something else happening. Not too long from now, we're going to be encountering a lunar eclipse as winter closes out on March 14th. It will be a total lunar eclipse. And a tool for that you can use is right here. This is called timeanddate.com. And in Google, you can literally just type in time and date lunar eclipse, and it'll bring you right to this. You may have to put your location in the upper right, but otherwise it'll come up with this nice tool set of what to expect for the total lunar eclipse on March 14th and when to expect it. Now, what's great about total lunar eclipses versus solar eclipses is they happen a lot more often. This is the eclipse map, and the darkest part of that eclipse map is showing you all the regions that will see the total eclipse. Beyond that is partial eclipse. So there's a lot more room here, whereas for a solar eclipse, you just get this, a total solar eclipse, you just get this narrow band across the sky, across the US for the last one. But they do happen, total solar eclipses happen across the world, but they're much more localized. So if you come down here, you can actually scrub through. From the beginning of the eclipse, it goes through the stages. So this is before the eclipse starts, right here in this region. And then you get to the penumbral eclipse. This is when you will just start noticing the moon starting to fade. The penumbra, you can actually see a lot of examples of penumbra around the room, just looking at the shadows. With a shadow, you'll usually have a very dark part, and then around it you'll have a fuzzier part of the shadow. It kind of fades and gradients out. That's the penumbra. So the penumbra is the lighter part of the shadow. The umbra is the dark shadow. And that's where the partial eclipse comes in. So here you can see it getting a little bit dimmer, knocking down the brightness of the moon a little, but as the umbra approaches, it starts to get darker. You're actually in a shadow at this point. You'll notice the moon start to turn red, and that's your total eclipse. So maximum total eclipse begins at 2:26. Oh yeah, that's right. This one is an early morning one. So maybe plan around that if you want to see it. The maximum eclipse is at about 3 a.m. So starting at 11:57 p.m., maximum at 2:58, and it ends at 6 a.m. All you really need to do is make it to this point. Make it to the total eclipse so you can see the entire moon turn red. Why does it turn red? One way to think about it is it's as if every sunset and sunrise on Earth is happening at the same time on the moon. What I mean by that is you have indirect light passing around the Earth from the sun during a total eclipse. And when you look in the sky, even after sunset, but during sunset too, what color is the sky? Is it blue or is it red or pink? What do we think? Yeah. Yeah, red or light pink. And that's why the moon is red. That indirect light from the sun that's coming at the sides from Earth is passing through the atmosphere and hitting the moon. And that's what turns it red. So that's what makes a total lunar eclipse really exciting. So this is a great tool to try. You can do this in Stellarium too. We could skip ahead to March 14th and watch it there as well. But this is March 14th into the 15th, starting at 11:57 p.m. Just barely March 14th. All right. We might not make it through all of this, but that's okay. That's not what I want. I want to scrub here. Let's go to planets next. At this point, I'm just going to share it like this. I don't need the present view. There we go. All right. So, what planets are out? Let's just get right down to it. There are 4 visible planets out right now, and when we say visible here, we mean visible to the naked eye, to the unaided eye. No telescopes, no binoculars, just looking at the sky. Now, you're not going to see detail with your eye, but you will see the bright point in the sky that represents the planet. One way to tell the difference between planets and stars is that stars twinkle. The song's true. And planets do not. Planets are stable in the sky. Nice, stable, almost like a light bulb in the sky. So that's one way to tell. They're usually pretty bright compared to the stars nearby, because there's only a handful of really conspicuous stars, meaning really fairly bright stars comparable to a planet. But you may say, okay, hang on. Why are they in this order? Venus, Saturn, Jupiter, Mars. That's not how they're ordered in the solar system, right? Well, this is approximately how they're ordered in the sky and really how you should prioritize observing them. Because on this side, Venus and Saturn, they're going to set first. They're going to get lower in the sky earlier on. And then Jupiter and Mars are on the other side of the sky, so you have more time with them. These objects are more eastward. These objects are more westward. Okay, so that's why they're ordered this way. Also, what's neat is that Venus and Saturn are heading towards a conjunction. In fact, right now they're already pretty close. I think it's the 21st is the day of the conjunction, which is when they'll reach their closest point. They'll be about 2 degrees apart. 2 pinkies apart. So in binoculars, you'll be able to see them together, and maybe just about able to see the rings of Saturn and Venus, which I'll show you in Stellarium. What's special about Venus. Actually, you can see it here. I forgot the picture shows this. The picture of Venus, that one was taken around daytime as it was setting. So that's why the sky itself is pretty bright. But it's this little crescent that represents Venus. Because Venus is an inner planet, it goes through phases, just like the moon. So you'll see it go from a nearly full disk Venus to a gibbous Venus, which is more oval in shape, to half Venus and crescent Venus. And probably the most dramatic is when it reaches this crescent phase, which is it is in now, but will continue to sharpen that crescent as we head into February. Saturn is interesting too. There's so much interesting things happening with these planets this winter. Saturn its rings are starting to go edge on. So those rings are getting smaller and smaller from our point of view. And when they do go edge on, they disappear. Now when that happens, unfortunately, it'll be too close to the sun in the sky, so we won't be able to see that effect. But if we could, you would just see the planet itself. You would not see the rings. The rings are so thin that they completely disappear when viewed edge on from our distance. So fascinating. Jupiter here, you can see this image, has the great red spot in it. This was taken at, actually, all 4 of these were taken at Kopernik. That's why they don't look as sharp as something like from the Voyager spacecraft that was right up close to it. But you can see the great red spot. That's a big hurricane system on Jupiter, bigger than the Earth. Over here we have a shadow from this little moon here. I think it was Io when we took that picture. So this is the moon Io that you just barely make out as this little dot, not on the surface of Jupiter. It's orbiting around. It's a moon. But you can see the shadow. This is a solar eclipse happening on Jupiter. So that dark shadow would be, looking up, Io would be completely covering the sun in the sky, if you could stand on Jupiter at all. And then on Mars, January 16th was the opposition of Mars, the close approach of Mars. This is the best time to observe the red planet. Because otherwise, when we're too far away from it in our orbit around the sun, it's too tiny and too dim to really make out a lot of detail. But during opposition, we get features like this, Syrtis Major, a dark feature on the surface of Mars. You also get to see polar ice caps. So this is the south pole of Mars right there. So let me show you where these are in the sky with Stellarium. And what feature? I don't know if I'll be able to add view settings. Ecliptic, there it is. Okay, we need that line. So this line that I just marked is in view settings, and you can check that box for ecliptic. We'll talk about that as we discuss the planets. But let's go around this way. The nice time about the winter season for our location is that the planets are really high up in the sky compared to where they would be in the summertime. The ecliptic would be lower during the nighttime in summer. And all the planets and the sun can be found along this imaginary red line you're seeing, this arc across the sky. It does go all the way around, and what that red line represents is the path of the sun throughout 1 year here on Earth. So the sun will travel through this line and travel through the constellations. If you're wondering what the definition for your zodiac sign is, it's when the moon is in a constellation like Taurus at that point in the year. So for me, I was born in February. My zodiac sign would be Pisces. And at least a few thousand years ago, the sun would be in this region here in February. Now, that's not the case anymore, which is kind of what makes zodiac signs, in astronomical terms, there's not much interesting about it, because it changes over the course of astronomical history. But if you're wondering the definition, that's where it comes from. It's when the sun intersects that constellation. So the sun's traveling through, and that's what from the astronomical standpoint, we are interested in these because that's showing seasonality. The view of the constellations change through that ecliptic throughout the year. So sometimes in February, you really won't be able to see Pisces because the sun's too close to it. Wait 6 months, Pisces will be in the sky. So that's some interesting facts about the ecliptic. What the ecliptic also represents, beyond the path of the sun, is where you'll find the planets and our moon. Why is that? Well, when the solar system formed, actually this is where my poster comes in. And you are welcome to take one of these after the presentation here. This is an image from the James Webb Space Telescope. And for those on the stream, I'll kind of show you here. And everyone else, I'll come around. What you really want to look for is right at the center, there's this line. This is a protostar right in the center there. This is an early star forming, very early stages of its life cycle. And around that star, you have this line, this small line at the center. So look for that. It's a horizontal line in this image. Over here. And that line is a little solar system forming. That's how powerful the James Webb Space Telescope is. It can see the formation of an early solar system. It's called a protoplanetary disk. And that's what forms after a star really starts beginning to fuse and ignite. And that disk is where all this star's planets will come from. It's this disk of matter. Eventually, gravity will start pulling in to build bigger and bigger objects, and eventually you'll get planets. That's what our early solar system looked like as well. And because it's a disk, you start with that what's a protoplanetary disk. All of the main planets fall along that disk. It's all pulling material from the same plane in the solar system. So that's why we get all of our main planets along this line. It's representative of how our solar system exists today versus how it formed early on. And that's evidence for how solar systems form. So if you want to take that picture from James Webb home with you, we'll have them off to the left-hand side on the table there. All right. So looking in the western sky, we have Venus and Saturn. And you see, this is why I want to kind of get you outside. So Venus and Saturn are setting in the western sky right now. Look how close they are. They'll continue to get closer and closer over the next few days. Saturn and Venus. A really cool thing with Stellarium too is you can come down here, center, and zoom in. See how thin those rings are looking? This is not the best time to observe the rings. That image we had in the slideshow was, you saw a little bit more of them, and you could just about make out this little patch called the Cassini division. On either side, it's a kind of almost a hole of matter, lacking of matter in the rings. But they are so thin, and they'll continue to get thinner heading towards March. All right, Venus. Notice it tells you its position as well. That's our ABCs right here. Magnitude. You do have distance measured here. You have your equatorial coordinates there. Oh, look at some satellites. That looks like Starlink because there's a couple of them in a line, but perhaps not. Then altitude and azimuth coordinates. So there's our ABCs right there. But let's go to Venus, zooming in, and you can see it's just past its half phase. We're starting to get that crescent shape. If we advance time here, going day by day, see how it gets bigger? We're at the same zoom level. It's getting bigger because it's getting closer. And what's fascinating about this too is if you watched the magnitude, I'll go back in time again. So today, the 17th, it's at a negative 4.37. And come mid-February, it's around 4.5. Is that brighter or dimmer than it is today? Yes. Brighter, right? Because we got a larger negative number, right? So it got brighter despite it moving further along through its phase, its crescent. So at least leading up to February 15th or so, it will continue to get brighter as it gets closer, despite it getting a smaller crescent. And then as you go forward, eventually you'll start dimming again as you head into March. March will still be pretty bright, and you'll get this super bright, thin crescent in the sky. And that's perhaps the best time to see Venus. The reason being, there's not much to see on the surface of Venus because it's cloudy all the time in the sky. We don't really get to see its surface very well. All right, I got to wrap up here. So let me just see if there's any final points I want to talk about. If we zoom out here, we're back to current date and time. I just want to show you where Jupiter and Mars are right now in the sky as well. Jupiter's here, Mars there. And there are 2 other planets out as well. This is Uranus. That's the Roman pronunciation, by the way. And then we have Neptune is somewhere around here too, but it might not show up. And there's a good reason for that. It's because both of those objects are really dim. Let's search for it and see where Neptune is. Is that? Okay, let's see. Neptune. That's the search function for you. And you can see, yeah, there's Neptune. And you can zoom in on it in here and see what it looks like. But in a telescope, you won't see that. You'll just be able to make out some color detail. It'll look bluer. But you won't see the disk very well of the planet, and you definitely won't see surface detail for either of those 2. They're just too small by comparison and too far out in the outer solar system. You might also just be able to make out the moons of them. That's possible. More possible for Uranus than it is for Neptune. All right. Any final thoughts here? Out of the deep sky objects, let's just take a look at Orion Nebula. I don't need that. I clicked the wrong one again. Just this one. The Orion Nebula. This is just about visible to the eye. We can point it out for you as well. Their constellation Orion is really nice to observe this time of year. And the nebula itself is among the brightest deep sky objects you can see. In a telescope, you'll be able to make out its bright core where stars are being born. This is a stellar factory. It's before this phase. This is the protostar. This is the stellar factory that's churning out these early stars. And that's brilliant through scope. And this was also taken here at Kopernik through our 6-inch at the time. Cameras do a better job with these deep sky objects compared to your eye, but this is still a really dramatic one. Okay. And final thing. I'll show you these 3 apps as well. These are downloadable for your smartphone. Stargazing app, Starwalk, Sky Guide, and Sky Safari. This is in approximate order of complexity. These 2 are very similar, just slightly different UI designs. So kind of pick your favorite there. Sky Safari is more advanced. So if you're looking to jump into a new level of these sky map applications, this has powerful tools like even being able to control a compatible telescope with that app. So this is the advanced one, but start with these if you haven't tried one yet. You can also, of course, capture the skies with your smartphone. Oh, I keep doing that. These are some images captured with a smartphone of deep sky. So focusing on stars, you have this little object here. That's the Andromeda Galaxy. This was taken a few years ago, so even with newer smartphones, you should be able to even capture more. You need to use night mode on your phone to do these. And then on the right-hand side, we have the constellation Orion. Here's Orion's shoulders, the head, the legs, and this is, oh, I should mention the belt too. 3 stars in a row. That's easy to find. And then the camera's just picking up the Orion Nebula. Again, we can point that out to you in the sky tonight. So try out night mode even tonight. You can do it handheld. It works better with a tripod or propping it up on something, but try and see if you can capture stars tonight. And finally, as we close out, I do just want to mention what Drew had mentioned earlier, and that's Winter Star Party coming up on March 1st. So look forward to that. That's our next major event, and hopefully we'll have clear skies like tonight to enjoy what's out there. Planets will still be out, and I think, yeah, that we also placed it around when we have dark skies too. So no moon in our way either, which is good, unless you want to observe the moon, but the moon's out plenty of time. So we like our dark skies, especially during star parties. All right, and clear skies, everyone. I think maybe we can save Q&A for, unless we have YouTube ones.
There was one question on the chat from Linda, and she said, NSL question mark.
Oh, Night Sky Live. We have our FNL, Friday Night Live streams, which is what we're doing right now for those viewing virtually. And we have NSL, which is Night Sky Live. So they're asking, are we going to have a Night Sky Live?
Right.
There are enough events coming up. A lot of planetary stuff happening, like we said. There's the conjunction coming up. I would say the most probable one that we'll do is the lunar eclipse coming up on that March 14th to 15th timeline. So usually what we do with those Night Sky Live programs is we'll do a live view through our telescope. We'll have some commentary, and then afterwards we take that footage from the scope and we create a time lapse, so you can watch the eclipse happen over just a minute or two. So look out for that in March.
Any questions here? Otherwise, the
got-
only comment we had from the YouTube was YouTube said, "I had no idea Stellarium could be run in a browser." So that's actually a great way to get started, I think.
Yeah, that's the better path. If you're new to this, and you download the application to Windows or Mac, it's going to be really overwhelming. Use the web version first to get adjusted, and then you can look for more features downloading. Yeah.
All right. Well, at this point, we have a rule here that you can't leave Copernik until you look through a telescope. So it's possible that Venus may still be around, so definitely let's go and see if we can check that out first. But I think I'll have to find out from the Kopernik Astronomical Society, the group that are here, that's their club is based out of here. They'll be very happy to show you what we've got in the scopes and answer your questions. So thank you very much, Jenny, for another great presentation.
Thanks, everyone. And don't forget to grab a poster if you'd like one up front. They're just off to the left side there.
And put a place marker in your calendar for the Winter Star Party, March 1st, here at Kopernik.
We'll see you then.
Take care.